ball hit the ground without air resistance? In school, you might have heard of several ways to address this problem. One would be to use the Suvat equation, but the other would be to use energy. Because the ball is stationary at the top and maximum energy by the bottom, what we can do is take the gravitational potential difference between the top and bottom and say all of that energy goes into kinetic. This is a commonly known exam trick, and sadly, this only works because all of the potential energy is going into kinetic, or, if I was throwing the ball straight up, all the kinetic energy is moving into potential. It doesn't work all the time, or does it? What if I told you there is a way to do this trick all the time? And not only that, this trick turns out to be the most powerful and most commonly used method of mechanics, replacing Newtonian mechanics in higher levels of physics. Today I want to talk about Lagrangian mechanics. But first, we need to talk about Newtonian dynamics, and before we talk about that, we need to talk about what mechanics is. Mechanics is the study of motion. Anything that moves or does anything will be described through mechanics. Quantum mechanics describes quantum things, classical dynamics describes classical things. Newtonian mechanics is arguably the first mechanics that has ever been widely used. Newtonian dynamics describes the world with forces. A total force towards the east will make the object accelerate towards the east via F equals ma. To find this total force, we see all of the possible major forces that are acting on this object, and we take those into account. Stuff like air resistance, gravity, collisions, magnetic fields, all these things create a force on the object and try to accelerate it in their direction. If we just imagine all the arrows that they would produce, if we just sum them up like this, using some vector addition, then we'll be able to figure out the actual direction the object will go in. Newtonian mechanics can perfectly describe almost everything in the universe, so why are we replacing it then? Why do we desire a new form of mechanics? The main reason is because vectors are annoying to work with. Compared to numbers, which can add, can multiply in very intuitive ways, vectors can really only add. It's possible to multiply a vector by a scalar, but multiplying a vector by a vector is a massive pain. Also, the equation F equals ma is differential. This is a problem because differential equations can only tell you what's going to happen next. A force tells you where the object is accelerating now, not where it will end up. There are many situations where we only care about what the object does at the end, not all the faffing about in the middle. So when Joseph-Louis Lagrange created the theory of Lagrangian mechanics, you can imagine people were really excited. In the 1700s, Lagrange noticed something very interesting indeed. Let's imagine the ball example from earlier and see what the ball is thinking as it tries to fall. Why does the ball want to fall? Because it wants to lose potential energy. Why can't the ball fall? Because it doesn't have any kinetic energy to move to a place of low potential energy. Therefore, there is always a tug of war between the amount of potential energy something has and the amount of kinetic energy something has. If we just take the kinetic energy and subtract it from the potential energy, we get this difference, the Lagrangian. The Lagrangian is a little different to energy. Energy would be kinetic plus potential, and that is conserved. The way the Lagrangian is used is actually to define a thing called action. If we want to find the action of the ball, we keep track of it over time and sum up the Lagrangian. The total sum of this, or the integral of the Lagrangian over its path, is the action. The action is called S for the sole purpose of confusing people. But if you considered every possible path the ball will take and choose the path that has the least action in it, it turns out that's the path the ball actually takes. This may sound like we just got a roundabout way of doing mechanics, but unlike Newtonian dynamics, I can start and end in any two positions. As long as I can find a path that has the least action from the start to end points, I have the path the particle will actually take. To find this path of least action, Lagrange went to his good old friend Euler. Yes, Euler, the guy that has everything named after him. Together, they developed the calculus of variations and made the Euler-Lagrange equation. There's plenty of interesting videos describing how it's derived, so I'll just go over how to use it. Let's try the ball example. The ball has the kinetic energy of half mv squared. It has potential energy mgh. To use the Euler-Lagrange equation, we need to use partial derivatives. A partial derivative means take the derivative of this variable, but keep all the other variables constant. It's a little bit weird to take the derivative of position without velocity, but that's just how the Euler-Lagrange equation works. The equation we get out of the end is acceleration equals to g, which is exactly what we wanted. Sure, in this situation we need to use a bit more calculus to get the final solution, but the technique we just used is general. Think about how easy it is to build a Lagrangian of a super complicated system. One of the most complicated Lagrangians of all time, the standard model Lagrangian, is literally just the kinetic energy term for a relativistic particle plus the three forces for potential. It's no surprise then when it comes to the most modern theories of physics, all of them are just Lagrangians. If I wanted to combine two completely different systems of mechanics, it's as easy as just adding the Lagrangians together. Before we end, what happens if the Lagrangian doesn't have a variable in it? Well, then the partial derivative would be 0, and we're left with this. looking carefully and seeing that this corresponds to momentum, and oh, if the Lagrangian doesn't have the variable x, then the momentum of x is constant. A very clever person looked at empty space and went, hold up, the laws of physics, if they were a Lagrangian, would not depend on position or time. It would be quite stupid for an experiment on Sunday to be different to an experiment done on Monday. And similarly, it doesn't matter where you do the experiment, the physics should still be the same. Because changing time and position, so-called translational symmetries, do not affect the Lagrangian of physics, it ends up with the laws of physics requiring both energy and momentum to be conserved. As long as space doesn't change and space is equal everywhere, energy and momentum are conserved. This is Noether's theorem. Lagrangian mechanics is the first juicy thing that students learn when coming to university. It's therefore quite sad that it's not shown off just how universal it is. I mean, whenever you do, like the kinetic to potential energy trick that I mentioned in the beginning of this video, you are implicitly using Lagrangian mechanics. There are a surprising number of things that just aren't taught that well that I plan to make videos for. Thankfully, 3 Blue 1 Brown Summer Contest is here yet again, pulling me out of my ass to actually do something productive during the summer break. Thank you very much for watching, and have a good evening.